He loves chemistry 'cause it's fun. If that makes you crazy, then he's the one to teach you chemistry 'cause it's fun. He's chemistry coach. He's chemistry coach. I'm not dead yet. And though that day will come eventually, for as long as I'm alive, I'm happy to be your chem coach.
Why, you stop that right now, you young chemistry student. I can't believe it. What? You're spelling sulfur with a PH instead of an F. Well, that's downright un-American of you. You'll never make the Chem Olympics at this rate.
Hi, welcome to Chem Coach with Coach Powers, where my goals are to help you to have fun enjoying the beauty of chemistry. I want you to have many aha moments, and I want you to learn the sport. Is this a sport? Learn this subject way better than I did when I was in chemistry. Enjoy. All right, so before we get started, let's go ahead and do a little bit of review of kinetics and maybe tie that into what we're going to jump into today. So first of all, when you're thinking of kinetics, you're thinking of motion, right? So take that to the next step. You've got to remember that there's probably going to be different rates that reactions will occur at when the particles are in different rates of motion. If we have more particles, we've learned that we might have a different reaction, and so the rate of the reaction might be affected as well by certain numbers of particles. So some particles matter more than other particles. Generally, as a reaction occurs, you're going to have a decrease in the concentration of the reactants as it becomes part of the products. And generally, you're going to have an increase in the amount of products, right? That's if the reaction is going in a forward direction. Well, reaction kinetics, or chemical kinetics, deals with how fast these changes take place. So, we are going to study reaction rates and reaction mechanisms in reaction kinetics. That's what we're going to look into. Now, if you look at this reaction here, you can see that we have on the far left all of the reactants. They're all the same. Those particles are identical. And then you notice that as we're proceeding to the right side of the reaction, we end up having more particles becoming transformed into the products. So these reactants on the left are being broken up and they're being turned into the products on the right. On the right, you notice we still have some of those reactants left over, and that's because they weren't used up in the reaction. So in the past, we've looked at that reaction and we've seen that it seems to be straightforward, but we don't really think about that intermediate step, that middle box there. And so now with reaction kinetics, we're going to think about that middle box a little bit more. Think about the intermediary steps that are taking place there. So the first reaction that you guys are going to be looking at is this reaction of nitrogen monoxide with oxygen to create nitrogen dioxide. And it seems pretty simple on the outside, but when we dive in, you're going to see it's a little bit more complex, a little more exciting. All right, so this lesson is on reaction kinetics. We're going to learn three basic terms: reaction mechanism, intermediate, and rate determining step. Reaction kinetics, and particularly the rate determining step, is a lot like a car manufacturing plant. You're going to figure out how many cars are being made as you watch them go out the garage at the end. Now, that is telling you how much is being produced. If we're talking about chemical, how much chemical is being produced, how many cars are flowing out the end. But you could also determine how many cars were flowing out the end if you were counting the number of windshields that were coming in, for instance. Since your number of cars being made is going to be limited by the number of windshields coming in, then you could determine that rate with either of those mechanisms. And that's what chemistry does here with the rate determining step. If there's one particular step that is going to be limiting how much chemical is being made in the products, then that one particular chemical is going to be the rate determining step. So by the time we're done with this lesson, you should be able to define a reaction mechanism. You should be able to identify the intermediate in a multi-step reaction. And given a rate determining step in a reaction, you should be able to predict the changes in that reaction rate for a concentration change of one of the reactants. So if I increase the number of windshield wipers coming in, is that going to affect the number of cars coming out? That kind of thing. Now, what I love about reaction mechanisms is that they tell you a little bit more about chemistry that you didn't really know before. That there are little steps happening underneath the main chemical reactions that we hadn't really thought about before. One of the things that I had learned after years of having some of my students do a particular experiment where they were trying to get a particular amount of product out was that there was a whole bunch of other reactions taking place before my product ever came out, and that was totally affecting their results. And after so many years, I'm finally like, my students really cannot be doing this that badly. And sure enough, they weren't. It was just that I didn't realize there were sub-steps taking place that were affecting everything. So it's neat to see that there are some sub-steps sometimes that we don't realize are taking place. It's also... So first of all, we want to talk about reaction mechanisms. And if we think about a reaction, a lot of times we just think of a chemical equation. We've gone through and seen a lot of these. We just have one final reaction that it's actually quite a bit more complex sometimes than what it seems to be. As an example, I'm going to show you a reaction that would give you the product of NO2. And we're starting with NO. We've got 2NO, and we're going to react that and ultimately going to get 2NO2. But there's something that's happening behind the scenes that we don't see. So if you look in this reaction, you can see 2NO2 gives you N2O2. They detect this in the intermediate of the reaction. All of a sudden they find that this chemical is in there. And then that N2O2 then reacts with O2 to give you 2NO2. And so this whole process is called a reaction mechanism. What we're actually seeing here is that there is a subset of steps that are taking place. And because many reactions have these little subset of steps, it will often determine how fast this reaction goes. So the series of steps is called the reaction mechanism. And even though the reaction appears simple, sometimes it might be more complex. It's essential to understand that this reaction is taking place, these sub-reactions are taking place because there's a lot more involved, and if we want to figure out how fast the reaction takes place, we have to understand what's happening behind the scenes. So we want to define a few terms: intermediate and rate determining step. The intermediate is a chemical that's made in one step, but that it is actually not found in the final product because it gets used up in the next step. So intermediate, substance that forms in one step but then it's used up in a later step. And then the rate determining step, which is the slowest step of a reaction. The overall speed of the reaction is going to be determined by how fast the slowest person is. Okay, you got a bunch of people chained together and they're trying to run a race. The slowest person is going to determine how fast that final finish is going to be done. This allows us to predict something called the rate law. Now, we haven't talked about rate law yet. We'll talk about that later. But that is what we will use, this rate determining step, to figure out what the rate law is. So in this example, once again, you can see up here on the screen that we've got 2NO plus O2, both gases, giving us 2NO2. And we find that this N2O2 is detected during the reaction, even though it's not one of our final products. Now that first step is a slow step, the NO plus the NO making the N2O2. So if that's the slow step, it's probably going to be considered the rate determining step, right? So step 2 is the faster step. N2O2 plus O2 gives you 2NO2. Overall, the reaction is, as we stated in the beginning, 2NO plus O2 gives you 2NO2. But the slowest step is going to be the rate determining step, and so that's that first step. Here's another illustration of that so you can see what we're looking at here. You've got those blue spheres and the red spheres. The blue spheres are nitrogen, and the red spheres are oxygen in this case. And so you can see the chemical reaction taking place in this illustration. Okay, so let's practice an example. What I want to show you here on the screen is a hypothetical reaction between A and B. It's a two-step reaction. And you see A and B are going to make AB, and then in step 2, A and AB are going to come together to make A2B. Now, your net equation ultimately is going to get rid of the intermediate step, right? So if you look at the products of the first reaction and the reactants of the second reaction, you can see that AB is in both of those. Those will cancel out. So your overall reaction is going to be A plus B gives you A2B, and of course it's going to be two A's, right? So it's going to be 2A plus B gives you A2B. Now, our intermediate in this case then is AB, and assuming step 1 is the rate determining step, what does this mean for our reaction rate? Now, if you see A in brackets, that means it's talking about the concentration of A. If you see B in brackets, it's talking about the concentration of B. So, if we take the concentration of A and increase it, what happens to the overall rate of the reaction? Well, we're going to learn a little bit more about this as we talk about the actual K value and the R values when we talk about this in determining our rate laws. But the rate of the reaction, if I have more A, it would make sense I've got more A for the B's to collide with. Remember, these reactions are taking place because of collisions. So if I have more A's for the B's to collide with, then there's going to be more possibility for AB to be made. So if I increase A's concentration, I'm going to increase the rate of my reaction. If I have more B's, same thing's going to happen there, right? I'm going to have more collisions with the B's and the A's, and so more opportunity for collisions means more AB. Therefore, I now have an opportunity for my slowest step. My rate determining step is faster, so my overall reaction should be faster. Okay, so let's look at another example. In this example, we have step 1, which has A and A coming together to make A2, and then it has A2 and B coming together to make A2B. So again, look at the two. You can probably determine the rate. You can probably determine the rate determining step, and it's going to be the one that's the same on both the products and the reactant side, right? Products of the first reaction, reactants of the second reaction. Those are going to cancel out. Your overall reaction is going to be A plus B gives you A2B, or 2A plus B gives you A2B. So your intermediate is A2, good job. And assuming step 1 is the rate determining step, what happens to the overall rate of the reaction if I increase, right, in brackets, increase my concentration of A? Well, that first step is our rate determining step. And if I have more A colliding with more A, it stands to reason I'm going to have more A2. So that should make my reaction speed up. If you change something in your rate determining step, if you change concentration in that rate determining step, you should be changing the rate of your reaction. What happens if, in this example, if I increase my concentration of B? Is B in the rate determining step? Nope, it's not. So the rate determining step is still slowing the whole reaction down. It doesn't matter how much B you have there. It actually is just all about the A's being able to collide. And since the A's are not colliding at any faster rate, then you would assume that your rate of the reaction is not going to be changed. Okay, so if B's concentration is increased, then the rate is not going to speed up. In fact, you might even be able to argue that B's being in the way might slow it down a little bit. Not sure what we're going with in that particular example there, but it's definitely not going to speed up. Good job. Okay, so to summarize what we've learned in this little mini lesson, we can now describe what a reaction mechanism is, right? It's a series of steps that is going to describe the overall reaction. And if I were to give you a reaction mechanism, you would be able to identify the rate determining steps, okay, and the intermediates. Now again, we're always going to tell you this step is the slow step, this step is the faster step. If we have multiple steps, we'll tell you which one's a slow step. And then from that, you can determine whether or not the overall reaction might speed up based upon those number of collisions. Okay, great job. Thanks for... All right, so that does it for reaction kinetics. Now, please go back and watch anything that you didn't understand. Go back and go through it again. Check out some of my other resources, some of the links that are going to be below. And if you have any questions, please write in the comments and I'll try and get back to those as well. I hope this has been an enjoyable experience for you, and don't forget to keep on chemming on.